Well, hello everyone. Welcome to our second event of the 2021 calendar and into the kind of into the second half of the Encode hackathon. I'm delighted to be joined by Alex, who is CCO of Beam, and he's going to tell you all about Beam. He's going to tell you about how to do their challenge in the hackathon. There's still plenty of time to do it, and yeah, cool things to look out for. With Beam. As ever, guys, I will be recording this event and we will put this along with the slides up afterwards in all the usual places. If you do have any questions, so use etiquette, please put them on chat and we'll try and get to them throughout the event, but mainly at the end. So looking forward to this. Alex, great to have you back. And yeah, over to you, sir.
All right. Hi, everyone. Thanks for having me here. There are actually a lot of people and I don't even see everyone on one screen, and I have a decent size screen. Okay, so let's get started with our presentation. We have with us joined right now Vladislav Gelfer, who is the lead developer in Beam, and he is the person who actually developed most of the things that I will be talking about. In case we get into very low-level technical stuff, he will help me with the things that I'm less familiar with. But the purpose of today's session is not to explain every little thing, because it's hardly possible within the 45-minute time frame that we have, and we have 15 minutes left for questions at the end. However, please do ask questions in the chat or raise your hands via the Zoom raise hand function, so that if something is not clear along the things that I'm describing, I would rather explain it along the way. All right, so let me share my screen here and open the presentation, and let's get started. Okay, so I hope everyone can see that, right?
Yeah.
Okay, so good evening, everyone. Hackers, I love this word. Welcome to the wonderful world of Beam Confidential DeFi. It's something very new. Beam is a confidential cryptocurrency which exists for the last 2 years. We have actually had our second birthday on January 3rd this year. Today we're going to be talking about the new technologies that we have been developing recently, basically the idea of adding more functionality, smart contracts, and building applications on top of our confidential blockchain. And with that, I would like to explain, like, step by step, build the entire overview of how we got where we are and what it all means and how it works. It's going to be a little bit heavy, I believe. A lot of information, probably, especially if you're not familiar with the things we've been doing and the protocols that we've been using so far. And once again, please ask questions if something is not clear. In Russian, they have the saying, there are no hard problems. There is just not enough vodka. So pour yourself a stiff drink if you're choosing, and let's get started. Okay. So as you know, there are several different types of cryptocurrencies in the world. And today we will look at two types, namely Bitcoin and Ethereum, which you are probably familiar with. And the difference that interests us in this specific case is that the fact that Bitcoin is UTXO based and Ethereum is account based. And these are two completely different approaches for designing blockchains. So Beam, just like Bitcoin, is UTXO based. So we will start with that. And the meaning of the word UTXO based is that we have our value on chain represented as the unspent transaction output. So basically, when we look at the chain, we see results of previous transactions, and each such result is called unspent transaction output. It's unspent because it was not spent yet, and it's an output of some previous transaction. And this is something very basic for Bitcoin. Of course, each transaction output results from some previous transaction input. And then when we create a new transaction, this transaction output becomes the input of the next transaction, and so on and so forth. And we have this tree of transactions, and each transaction converts some UTXOs from inputs to outputs, and then again. So one of the questions is where do the initial UTXOs come from? And it's a simple one, because they come from mining. Whenever a miner closes a block, he receives a reward, which is written on the blockchain in form of a unique type of transaction that's called coin-based transaction. And it's usually written in the block header, and it follows the protocol, how much coins does the miner have as reward in this case for each block, and usually changes over time. And in Beam, just like in Bitcoin, both are proof of work cryptocurrencies. So every time the miner closes a block, he receives a reward. And this is like how the new coins are born. And from there, when the transaction, miner creates a transaction and spends the coin base, it becomes another unspent transaction output on the chain. In Bitcoin, it works in a very relatively simple way. So each UTXO is owned by a specific address. It's not exactly true, because actually there are some cases like you have multi-sigs and other more complicated cases where the ownership is actually done by a script, the Bitcoin script. But we will take a look at the most basic case, that we have an address. And an address is just a transformation of some private key, which is random, and you may know it by the name of seed, or the 12 words or 24 words, depending on the algorithm. And then this private key is transformed into a public key by something that is called elliptic curve multiplication. And I suppose this is something also most of you are familiar with. Basically, we have this branch of mathematics that deals with it. We have an elliptic curve over some discrete space, and we select some generator point. We call it G in this example. And when we multiply our private key, which is basically a long number, a long scalar, by this point, we get a public key. And what is very interesting about this operation is that it is irreversible. So when I see your public key, I cannot derive your private key from it, even though I know exactly which point G you are using. In fact, this point and the elliptic curve that it comes from are standard and are known. Specifically in Bitcoin, they have this beautiful elliptic curve, which is called Jessica. No, I'm kidding. It's called SecP256K1. But it's a well-known curve which has specific mathematical properties. And in Beam, we use exactly the same curve as well. So then after we get the public key, we hash it in a specific way, and then we get these addresses that you are used to seeing in Bitcoin. And every time we look at the UTXO, we basically see that the transaction in Bitcoin is described as this kind of a condition, which says something like, please grant the right to spend the following UTXO to the person who knows the private key that matches the following address, or basically matches the following public key. So this is how in Bitcoin transactions are specified. And of course, since in Bitcoin, all of the information is completely public, when we look at the blockchain using Blockchain Explorer or any other way, we can see all of this information. What is the value of the UTXO, which addresses it belongs to, and of course, we can reconstruct the entire transaction graph and know where it came from, and all of the information is available. Okay. So it's very, very clear, and this is basically the standard from where we're like starting our journey, how Bitcoin works, the oldest, the first cryptocurrency, and the most well-known. Now, Beam is also UTXO-based cryptocurrency. However, it works differently because Beam, the idea of Beam is to be confidential. So we don't want just anyone to be able to see the information that exists on the blockchain. And the person who invented the protocol that we're using, the protocol is called Mimblewimble. It's a funny name coming from the Harry Potter world of things. It's basically the name of a spell which prohibits you from telling secrets. The author, by the way, is anonymous, and I believe he was a nephew of the former roommate of Satoshi Nakamoto, but that's just speculation. So this author created the following idea. He said, listen, instead of having this condition, this if, which is described in the Bitcoin script, let's just throw all of that out. And instead, we will use this formula that you can see here to encode our UTXOs. So what he said is basically the follows. Let's take the value that we have, 100 beam or whatever, and multiply it by some point on the elliptic curve. And then add to it another factor, which you can see on the left here, which is called the blinding factor, which is just a very long random number, this b, and multiply it by the different point on the elliptic curve, the same elliptic curve. And all of these points are known in advance. It's a public information. Now, as a result, we get this sum of two elliptic curve multiplications. And this structure is known as the Pedersen commitment. So if you Google Pedersen commitment, it's a cryptographic commitment scheme. And the idea of this scheme is that you create something that you cannot change in the future. So for example, I cannot change the V, the value of the transaction, without changing the C. C will always change with the change of V. And also, of course, I cannot know, unless I know these random B and V, I cannot know what value is encoded in this commitment. And now this structure basically represents a single UTXO, some random blinding factor, which is kept secret, of course, only the owner knows it, and the value of this transaction. Now, you can say, what about the address? Where is the address in this scenario? And the answer is that there are none. Basically, in Mimblewimble, there is no address or any other identifying information encoded on the blockchain. Okay. So how does these Mimblewimble transactions, how does that look like? So the transaction, and you can see here that the transaction is in quotes, and I will explain in a minute why, is basically just, let's take a look at some stupid example. Like I'm creating a transaction where I take my UTXO and I just split it in two different parts and I send it to myself, just for example. So I create a transaction input, which looks like that. And now I have some other transaction output, which looks exactly like that, but V's obviously are different. And I can also choose maybe the same B because it's my transaction, or I don't need to change it. And when we take a look at these transactions together, we see that if we summarize all of them, basically we take the sum of all inputs and the sum of all outputs, they should always sum to 0. Why? Because the value that I previously had, I just split it in two. I did not create new value out of thin air and no value disappeared during this process. It's just, simple addition or subtraction of the same amount of coins. So if all of these operations of inputs and outputs sum to 0, this means that the blockchain is valid. This means that no value was accidentally created or any value disappeared from the blockchain. And this is indeed how we validate the blockchain. We take all of the inputs and we take all of the outputs together. We summarize all of them. And the eventual result, it will not be 0, but it will be equal to the amount of coins that were created in each coin base for each block. Right? So if we have, let's say, for example, emission of 100 coins per block, it means that after first block, we have 100 coins, 200, 300, and so on. And obviously, the sum of all values should be equal to that number because there is no other way to create new number. Okay. Now let's take a look about a little bit more complicated example. When I want to send, for example, Vladi some coins in Mimblewimble. So obviously, I know this B, which is the blinding factor. It's also the secret key that allows me to show that I'm the owner of this coin. And I can just disclose it to Vladi and say, listen, that was mine coin. This is the secret. Take it. Now it's yours. But here we have a problem because now both me and Vladi know the same secret. So it's not exactly his. It's like kind of ours. And nobody knows who will spend it first. So Vladi would love to change this secret to his own secret that only he knows in order to be a proprietor, like, unique owner of this coin. So in order to do that, Vladi will have to choose a different secret. We call it B prime here, or B tag, and replace my secret, my old secret, with his secret that only he knows, and thus receive the ownership on the coin. Now, this causes a problem because if we have different Bs, the sum of all inputs and outputs will no longer be 0. It will be equal to some difference between these two random numbers that we have selected, and these are like huge numbers. So in order to balance this equation, we add a new entity. It's called the kernel. And in the most simple form, in the basic Mimblewimble transaction, the kernel is basically a difference between these two blinding factors. And now when we calculate this complete sum of all of these factors, including kernels, we will get to 0 again. And this is how, once again, we can validate that there was no new value created or destroyed during this process. Now, without going too deep into the technical details of how it's done, first of all, it's done completely off-chain. So on-chain, we only see these commitments. We see the commitments of the previous blocks and then the commitments of the next block. We do not see any negotiation between me and Vladi and how we exchange these keys. This is all done offline, off-chain. And it's done in case of Beam using a separate protocol. And this is what allows no identifying information to be ever recorded on the blockchain. And this is very important for privacy because it means that all you see is basically encrypted values without no identities. And it's not like you can take, very large supercomputer and analyze the blockchain and get those identities. You cannot get them because they're just not there at all. What you see is encrypted values, basically. So that's the only thing that is seen on the blockchain. However, the downside of this is that this process should be done interactively. So unlike Bitcoin, where you get an address from someone and you can send them money to this address, Bitcoins to this address, whenever you want, and you don't even know if this person is online or alive or whatever, reachable. Here, in order to create a transaction in the basic Wimble-Wimble protocol, you need both parties to cooperate and both parties have to co-sign using their signatures respectfully each of these components, and especially the kernel. And it's very important, and we will talk about this a little bit later again. It's important that both parties participate in the creation of the transaction and specifically the signing of the kernel. Any questions? How do we, anyone? Let me see.
There's a couple, I think are there any alternatives to an elliptic? They've said code, but I think they mean
code. I see the chat, but if someone has any other questions, please put them in the chat. Once again, elliptic curve cryptography is something very, very basic. It's been used for a lot of purposes. Whenever you see like HTTPS or this lock icon in your browser, it uses elliptic curve cryptography. It's basically the most known asymmetric cryptography where you don't have the same key for encrypting and decrypting data. Yes, Beam is quantum resilient, not in the scope of this lecture at all. We have an article about that, and I will gladly point it to you at the end of this session. Complicated topic, but we are. Okay, the questions are very advanced. All right, let's move forward. So why do we need all this complexity? And there are several reasons for that. The first one is obviously we get confidentiality. As you have seen, no addresses at all, and all the values are encrypted. But there is another interesting feature about Wimble-Wimble, and it's the idea that you can take all of these intermediate inputs and outputs. Let's say I send something to Vladi, and then Vladi sends something to Anthony. When we look at the blockchain, we don't really care about the fact that Vladi used to have something. We only care about the fact that I had it initially, and that currently Anthony has it. And we can omit in a way. So new node, when it connects to the system, doesn't really need to download all of this information in order to validate the blockchain. And it's a huge deal because, as you know, in Bitcoin, the blockchain size is huge. And if we take other implementations of confidential coins like Monero or Zcash, it's even bigger. So in Wimble-Wimble, not only is it not as big as Bitcoin, it's actually smaller. And the reason for that is we only care about the current UTXO set, the currently unspent outputs. And of course, we need all the block headers, all the coin-based transactions where these coins were actually born, but we do not care about the intermediate UTXOs. We do, however, store all the kernels because the kernels are needed to balance this entire equation. So we only need the kernels, the UTXO set, the currently unspent transactions, and the Coinbase in order to validate the chain. And it's called cut-through, and it's like one of the big features of this Wimble-Wimble protocol. Why it is so interesting. Now, what else, what other beautiful things can we do with this protocol? For example, we can create confidential assets. basically like tokens on Ethereum, right? Like the ERC20 contracts that you are familiar with. We do not need smart contracts for that. What we can do is basically take this structure that we have and just replace one of the generator points by another one. It's not so simple because they have to match specific conditions, but let's say we managed to find a new generator H1, and now this C2 encodes a completely different value. This, let's say C is Beam, and now I want to create Alex coin. So I choose a new generator and I create this C2, I call it Alex coin. And now we have two different tokens on Beam network, completely separate value, completely separate entities. And what's the beauty of it is that it inherits all of the properties of Beam. It's confidential by default. It works with cut-through. So I created a new coin, a new confidential coin in an instant. It's like one command. I don't even need to write any code for that. And of course, I can do it as much as I want. I can create any amount of assets. Now, in Beam specifically, there is another complication there, which ensures that when you create a transaction, not only there is no identifying information about you or the value that you're sending, even the type of the asset that you're sending is not known. So you see the transaction, you don't see what's in it at all. What else? There is a lot of things that we can do with these kernels because of the fact that they're stored in the blockchain forever and they're signed by all of the parties that participate in the creation of the kernel. We can use these kernels to do very interesting things. For example, we can add hash and time block information, HTLC as it is known, and implement, for example, atomic swaps, which we did. You can exchange Bitcoin for Beam in a completely decentralized way using atomic swap feature using these kernels. We can create relative kernels, which means that a specific kernel is valid only if another kernel is present on the blockchain. And we can use this concept to implement direct payment channels like the the Lightning Network that exists in Bitcoin. We call it the laser beam. But it's basically the idea that you can create a channel between two wallets and then send transactions back and forth with instant confirmation and only eventually settle on chain. Or we can create kernels with side effects, basically kernels that modify the state of the node, and then we can use it to implement Lilanto's shielded pool, which is a completely different protocol, but we managed to combine it with Mimblewimble, and it provides additional layer of privacy if you need. Now, these kernels with side effects can actually do something else. For example, let's say we have our standard Mimblewimble transaction. We have inputs, outputs, and kernels. And in the kernel, we write some kind of instruction which says, create some variable that will be equal to 2. And the node takes this transaction, parses it, and understands that this transaction would like to create a variable inside the node and make it equal to 2. Okay, so it's kind of a side effect, right? It's transaction that changes the internal state of the node. Or alternatively, instead of doing this assignment operation, we can call a function. We can create a function which is called setX, and then use this kernel to call this function. And inside the function will run and assign the value 2 to some global X variable. Okay, so these are called kernels with side effects because they change the internal state of the node. Now, we can complicate this a little bit further. We can create some class and wrap this entire thing in some container. And basically what we get as a result is a smart contract. Piece of code running inside the node, getting the results from transactions and storing it on chain. That's exactly the definition of smart contract as they exist on Ethereum, and you're probably familiar with this idea. So what we have here right now is some kind of a hybrid because we have started from the UTXO-based cryptocurrency like Bitcoin. And now suddenly we have this idea of a smart contracts within the same chain. And obviously inside these contracts, we can create accounts or anything else. So we have this kind of merged hybrid approach between the UTXO-based cryptocurrency as Bitcoin and now also the account-based cryptocurrency like Ethereum. Okay. Now, of course, in order to run these programs, we need some kind of a virtual machine, obviously, that can take this code that we have written, understand it, parse it, compile it, do whatever it needs to do, and then execute it on the node environment. So that's exactly what we've done. We have added Beam Virtual Machine. It runs WebAssembly. WebAssembly is a very well-known and popular stack of technologies that are used in the browsers and in many places, actually. It's an industry standard. There are a lot of tools and a lot of documentation available about WebAssembly. So we chose it because it is rather well known, and we believe more people know it initially than, for example, people that know Solidity or some other custom programming language used to implement smart contracts in different chains. And in our case, we have started with C++ because Beam is written in C++ and all our developers know C++. So C++ is being compiled by LLVM, which is this compiler toolchain family, into the WebAssembly code. And this code runs inside the virtual machine that we have added to our node. This is how it works as like the toolchain. So we have called these pieces of code, we have called them Beam shaders. The shader is the name that we have taken from the gaming industry. It's like this piece of code that runs on the GPU and changes, the colors and the shades in the three-dimensional image. And the reason we have called it shaders is because this is exactly like same analogy. This is like small pieces of code that take a transaction and do some modifications as a result. And also it sounds cool, like Beam shaders, Beam shade. That's also one of the reasons. And in this specific case, we're talking about the shader that is deployed on the blockchain, just like a smart contract. So the code itself is deployed to the blockchain, and it implements some logic that you can work with in order to create applications. And now, this is like the first part of the theory. So, of course, in the presentation that you will get, you will have all of these links to the resources, but I will go over that and just to understand what you're going to receive. And then we will see some code and some demos, like a little bit more in depth. So first of all, Telegram is the place where I am the most active. And this is my personal account, Big Romanov. You're welcome to write to me anytime you like with any type of questions. Maybe we will create a group, maybe not, depends on like what our goals are, but please do not hesitate to ask me any questions that you have about any of this. And also we have a dedicated group that we have created for BeamX, which is the name of these like new generation of Beam chain. And we have 2 support groups, and this one is specifically for developers. So all our developers are there, ready to answer your questions. All of our code is open source, so you can find it here on the GitHub repository. Specifically, the project you are interested in is this one, the Beam, the main project. We have building instructions for all platforms. Our code is multi-platform, so you can use it on Windows, Linux, or Mac. If you don't want to build it just yet, but you want to play with it, we have the latest release here at this link. You can just download the binaries and start playing with the node and the wallet. And here you have all of the instructions to get started specifically with BeamX. Now, BeamX is very, very new for us. And these instructions are far from perfect. So if you find any problems with that, see bullet number 1. And we also have the Blockchain Explorer for the testnet, the BeamX testnet that we have launched. So you don't really need to run your own node. You can just connect to this testnet and do all of the operations against the already running testnet that was created specifically for this purpose. Okay, let me take a look at the questions before we move on. Okay, there are a lot of questions here, but I will only answer those that are related specifically to what we're talking about, because I see a lot of general questions about Ethereum bridges and cool stuff like that, which, yes, we're working on, but that's a completely different story. Scalability. Okay, I will leave that to the end. I just want to make sure we go over all of the essential stuff before I get into cool stories about beam scalability. All right. So before we move on, let's get out of this PowerPoint for a second. Let's start with the how to run this. Just quick. It's not even going to be a demo. I will just show you how I've done this. Basically, what I've done is I went to this link. Okay, it doesn't open from here, but I have it somewhere here. This is the Blockchain Explorer, by the way. This is how it looks like. You see that we have just restarted the chain. We do it every once in a while because this is very active development branch and there are a lot of updates. So every once in a while, this network will be restarted from scratch. But here you can see that it's running. You can see the blocks as they're born, when, and inside these blocks, let me find an interesting example somewhere here. Maybe, no recent access to the contract. But if there is an access to some contract, you will see it inside this Blockchain Explorer, like what happened here. This was just some transaction. Now, this is the release page that appears in one of the links. BeamX, this is the recent release, just 14 hours ago. And what I'm doing is I'm downloading this package for my platform, basically. I'm interested in this one, Beam Node Wallet. So I'm on Windows, so it's going to be Win Beam Node Wallet. And when I unpack it into some folder, let's say this one, that's the code folder. Let's find where I did unpack it. Let me close all the rest, not interesting stuff. It's BeamX. So this is basically what I get. I get the binaries from the Beam node and the Beam wallet, and some configuration files, and the shader folder that includes all of the examples that I will show you in a minute that are already pre-built for you. You can, of course, modify it and build them. And just like, just as usual, the best place to start is open something that's working and start ruining it until it doesn't, and then fixing it again. So this is the same way here. Now, in order to run this, what I'm doing, first of all of the instructions on how to run this and how to work with that are there in the wiki page. But basically, I open several terminal windows. In the first one, I'm running a node. This is the node running. There was some transaction just now. Okay, and in the second, I open the wallet. And the wallet allows me to execute all of the commands in command line. We do have some graphical environment, but it's far from perfect. So for developing purposes, I'm using command line interface, and it's all documented in these pages that I have sent, and we'll send in the presentation. So let's see just one example. Right here, I'm running this wallet exe. Let me increase the font so you can see it better. 1 second. I always forget usually this part. Okay. So basically what we're seeing is this. I'm running the shader command, which allows me to access the shader. And I'm saying which application I want to work with. In this case, it's called the Vault. It's a very simple example of kind of a contract that allows you to deposit and withdraw funds. And they give it a few arguments that are also documented. So this shows me how many Vault type contracts is currently deployed on this blockchain. So I see there is one contract. This is the ID of the contract. And this is how I'm starting to play with it. Okay. This is just an illustration. Of course, everything, let me show you how it looks like. Here, let's start from the previous page. You have the getting started in the wiki, explains exactly what you need to download, how you need to run it. And then you see here that there are 3 examples for 3 sample contracts that we have created with all of the commands that you need to run. So everything should be pretty self-explanatory here. And of course, if you have any problem, we have complete documentation of the command line, and you can also contact us via any of these channels that you saw. Yes, setting up the development environment, and it's exactly the next step. So let's see how it looks in the code. First of all, one of the things that you see here in the presentation is the building instructions. And once again, we have the building instructions for all platforms. Here I'm on Windows. So the simplest thing to do is to just install Visual Studio Community Edition, in my case, download the BeamX branch of our Beam repository, and build it. And all of the building instructions, exactly what you need to install, the boost libraries, and all of the additional dependencies, everything is specified, and it's relatively simple. And now, once I have built my code, I'm going to the BVM folder. And we have here, the BVM is the Beam Virtual Machine. And under that, we have this shaders folder. And inside of it, we have all of these examples that I have described and a few others. So let's take, for example, the Vault example here. So you see here, there is a contract, H and CPP, it's C++, so that's how it looks like, the header and the C++ file. And if I open it, I can examine the code of the Vault contract, learn how it works, and then I can build it using a simple script that is included in the repository and described in the documentation, and deploy it for myself on the common BeamX testnet, and use it, basically. I know it sounds like several steps, but once you do this, one time and it works, everything else is basically more of the same. Now, for example, just to look how it works in the code, because the vault is a very simple concept, you just deposit funds and withdraw them. So we have this idea of an account. And as you can see, it's a public key, obviously, because I have to make sure that I can prove that this is my account. So I need to be able to provide a private key for that. And the asset ID, because as I said, we have confidential assets. So 0 is Beam and 1 is the first asset that you will create or whatever. And then we have the amount. And then we have two simple operations, which are basically doing exactly the same thing, just with a different sign. The one is called deposit and the other one is called withdraw. Now, if we look at the implementation of how this works, and yes, I am aware of the time. Let's see. Here, we have these operations to load the account. Now, this is a little bit confusing because you see here the method 0, method 1, and all this stuff. That's because we have each method mapped to a specific, eventually, a API call from external source. So it has this kind of weird enumeration. It's strange for the first like 10 minutes, and then you get used to it. So in this case, for example, the method 2 is mapped to the deposit call. And you can see it here, the vault deposit operation. And we load the account here. We make the strict add to make sure there are no like overflows. And I will talk about that in a minute, why this is so important. And then we just save back the account. So we have like 3 operations. Read, obviously, we read the variable, add to it, and then write it back to the blockchain. Okay? Now, this is an interesting part, the funds lock. So in this specific case, some money disappears from the blockchain. You send a transaction which has an input, and then this input is consumed by the contract. So the input disappears, and the blockchain needs to know that that happened in order to be able to balance the result. So there are no like sudden disappearance of money without any cause. So this is the operation which sends, which tells the contract to consume some of the inputs of this transaction. And in a second, we will talk about the wallet. The wallet should know that this is going to happen when it prepares the inputs for the transaction. The wallet should know, okay, some of these inputs will be consumed, so it's okay. The transaction is valid from my point. And of course, exactly the same is the withdrawal. Only in this case, some money suddenly appears out of the contract and is added back as an output to the transaction. So I'm sending the transaction without an input because I just expect to get the money back, and then the contract adds the output. So I'm kind of working with the contract here. And of course, anyone can deposit into my account, you're welcome, but only I am the one who should be able to withdraw the funds from my account, which is why here at the last line, you see this add signature for the account, which means that whoever is the owner of this account should provide the signature that this is indeed the case. Okay, I know it's not very clear, but as an overview, I think this should be okay. Now, one thing that is kind of not clear right now is how do I create those transactions? I mean, okay, we have a contract, it's deployed on the chain, but how do I access it? We saw that I ran some commands in the wallet, but what happens inside of it? Like how does it know what the contract does? I just wrote the contract. I created new methods, nobody knows about them. How does the wallet know how to work with those methods? What are the parameters? What are the, whatever. Now, in contrast to Ethereum or many other chains where these APIs can be made public because all the information is public, in our case, the information is kind of encrypted. Only the owner of these keys can know what exactly is written in those UTXOs and like what's happening. So it has to work with the wallet somehow because the wallet is the one who is managing all the secret keys. So in order to simplify this operation for the user, we allow the creator of the contract to create an additional part, which is called application shader or app shader, that looks exactly the same. It's basically some code compiled to the WebAssembly. However, it doesn't run in the node and it does not access the blockchain. It runs in the wallet. So we have this kind of the mirror architecture. There is a virtual machine in the node and there is a virtual machine in the wallet. And the one in the node runs the contract for the blockchain, the contract shader, and the other half runs the application shader, which knows how to create the transactions for this specific contract on the chain. And if we go back for a second to our editor, we will see that there is an additional file here which is called app.cpp. At this one, it basically describes all of the commands that our contract can execute. Now, what is very nice about this approach is that, let's say we have a contract that does this like vault functionality, but now I have several different vaults deployed by several different users, almost identical, maybe like some small parameter is different, like inside of it, but it's the same contract. So this application shader can work with all of them. I don't need like an additional one. I can deploy several vaults and use this specific application shader to access all of them. So here is the description of all of the functionalities that you can do. And when you run this view command on a specific contract, like, let me show you how it looks like. I hope I'm not forgetting something and it will work. Let's say I'm taking this specific ID of this contract. 1 second, I need it without the quotes. No, it's view commands. What's the command there? Let me check it real quick. I'm lost. What do? I go to documentation. Oh, I actually don't need any parameters to show that. I just delete all of the shader arrows. Okay. Here you can see exactly the printout of all of the commands that this specific shader supports, right? You see the create, to deploy, to destroy, the view accounts. In case of a vault, I want to see all of the accounts that I have, etc., etc. So basically the idea of the application shader is that provides all of this functionality. And when you look at the code, you will see that all of these functions that you saw in that list down there are actually implemented one by one here. Don't be scared by all of these macros. They are scary, but it's most of it. It's like boilerplate copy paste code, which we will eventually try to somehow hide and wrap. It's very like initial implementation. But what we do have at the end is these simple functions that like dump accounts, print of the accounts available, or for example, where is the deposit here? Somewhere. Account move is basically the function that either deposits or withdraws depending on the sign here. And then you have withdraw and you have the view and all of these methods implemented one by one. Now, this part is a little bit more difficult, but once again, we will help you to get through it, because it's basically the combination of, getting the values, signing them, and then creating the kernel. The most important function here is this one, generate kernel, because it takes all of these arguments and it creates the specific kernel for the transaction that will invoke your contract on the blockchain. Okay. So right now we have exactly 15 minutes left to the end of this meeting officially. Let me see what else we have here. Now, as you know, the goal of the hackathon is to implement the perpetual swaps applications, and I have included here some resources that are helpful in understanding what it is and how it should work. And now we can wholeheartedly move to the question part. Okay, so let me start with the some questions that I see here. Which sort of things are possible using this technology that we have created and that we want to implement? It's a great question. So let me give you some examples. Confidential stablecoin, which works similar to MakerDAO DAI, like algorithmic stablecoin, collateral based, something that you can implement using these contracts on our chain, these shaders. You can take and implement any functionality like Uniswap, AMM-based exchange. You can create lending platforms. You can basically create anything you can create on Ethereum. Only all of the transactions going in and out will be completely confidential. Okay, so the setup of the development environment, once again, it is described in details in our building instructions, which are here. Let me show it how it looks. Build from source, building instructions. The link will be in the presentation, how to build, the common part, and then for each platform. Wow, we even have CentOS 7.7 and CentOS 8 and Fedora, unbelievable, and Mac. Okay, cool. You can actually use anything. What else? Any other questions?
Should we go to the scalability one?
Yeah, the scalability one. So scalability usually has several meanings. One of them is transaction per second. And that is easily calculated. We have a block created every minute. We have 1 megabyte block size. And with our current transaction size, it is about 17 TPS. So basically like today's Ethereum in a way. Not the magical Ethereum 2.0, which will be extremely fast, but it's not here yet. This is the scalability in terms of transaction per second. However, another important scalability factor is the size of the blockchain. And in our case, the size of the blockchain grows as a function of UTXOs, so unspent transaction outputs, and not as a function of number of transactions like in Bitcoin. So on average, it's smaller. What is the current factor? So it varies, but we thought it would be 3 times smaller, but it's actually a little bit less than that, but it is smaller than Bitcoin for the same amount of transactions, of course. So you can remove all of these UTXOs that were consumed and just, synchronize without that. So once again, it's important to understand that this information is not actually deleted from the blockchain. That's impossible. The blockchain is permanent ledger. But if you connect a new node, you do not need to download all of this information. Okay. Bridges. Yes, bridges are possible, but this is a completely different topic. I'm going to be recording a video about that next week, about bridges. So you will welcome to watch that on our YouTube channel. Okay, I see that Angus has already answered some of these.
Yeah, what else we got? Yeah, there's people asking about, bridges, and also I think there's some idea about locking up Beam on one end and minting it in the other, but that is complicated.
Yes, it is actually one of the examples that we have here in our repository. Let me show you which one. It's called the roulette. When we have launched the BeamX on November 19th, just like last year, just a couple of months ago, we did this kind of social game It was not a real roulette. It was more of like social experience. No real money was involved and no one was harmed. But this contract illustrates how we can control an asset from the contract. So basically this contract is an owner of a new confidential asset that it emits as a reward for those who win in the roulette. If you look at this into this example, inside you will see the implementation of exactly how it works. And this is very powerful concept. It can actually create, like, for example, when we created confidential assets, like, okay, anyone can print them, like emit any amount, just like in ERC20, but now what? Like you don't have a contract behind it. So just one person that controls what happens, or like several people that control what happens to this coin. But when this is controlled by the contract logic, it's much more interesting, because now you can set, some predefined rules that kind of control the emission and the destruction of this coin. And this allows you to implement some interesting applications like stable coins or any other. So we have this example already here. And if you are like in the advanced part of this work, you can also take a look at that. Cool. It's not needed for this specific application that we are talking about.
Someone asked, what are the main differences between, they've put Monero, but I definitely think they mean Monero, Zcash and Beam.
Oh, so it's a very, very interesting discussion. I will answer it briefly, but if you really like go online, you will find the explosion of various opinions. Let's call it that. So basically, it's a different technology. Zcash is using zero knowledge proofs, so-called ZK snarks, for their implementation of confidentiality. Monero is actually using combination of several different technologies. They have the ring signatures and they have the shielded addresses, and in the middle, like they have this like something very similar, like to what we have also to connect all that. But and in Mimblewimble, we just have this Pedersen commitment as the structure of the UTXO, and everything else kind of falls from there. So all of the three are different, completely different implementations of confidentiality. It's very difficult to compare them. There are a lot of considerations, like what does it mean, and how like you can attack that, because you have passive attackers and you have active attackers, and it's really. By the way, Monero have great resources about that. They have very detailed videos that explain different attacks on Monero and how they are actually avoided by which technologies. We have all of the information about how it works for our implementation in our wiki as well, if you like want to really technical details. So yeah, it's a big topic, but basically it's completely different approaches.
Cool. So what else we got? Did we do the one about what we'd like to see built on Beam?
Yeah, as I mentioned, lots of applications, starting with confidential stablecoin, confidential Uniswap, and many
What do you think about stablecoin regulation?
First of all, I'm not sure whether he's referring to the most recent news about. So I read it. I didn't like completely understand what it means. Something about like OCC or something like that, allowing American banks to conduct like settlements in stablecoins. Maybe is this question about that? So basically, recently there was a lot of shifts in the regulation. Specifically regarding Bitcoin and stablecoins, obviously, because more institutional investors are going in, so they need to pay taxes, so they are going to lobby their governments to change the codes, and eventually they need to put this money in the bank. So the banks need to kind of accept money which is originated from crypto. Today, most of the banks do not really like this idea, to the point that they just don't do it. So you can bring some money and they say, okay, where is this money from? And you will say, okay, I sold some Bitcoin. It was 9,000 2 months ago, and now it's 31,000 or 35,000. So I made a lot of money. Let me put it in the bank. And they will say no. Like in Israel, this is how it works, for example. That might happen. So I think that the regulation is moving along with the interest and along with the amount of institutional investors that are working with Bitcoin and other cryptocurrencies.
Cool. Any other questions, guys, that you want to ask Alex for now? Awkward moment of silence. Was there anything else you want to show, Alex? Anything you didn't think you had time for, but we seem to have 5 minutes at the end?
No, I think I've, so let's say, as far as my purpose went to provide an overview of like the entire picture of how it looks like and how it works and how it's built and how it like the code looks like, I think I'm satisfied with this goal. At least we have covered all of the things that I wanted. Obviously, it's not near enough time to understand not even one of those things like in depth. And I would like to propose the following like continuation scenario. Take a look at the links that I have sent, download the binaries, play with it, try to do something. And if you run into any kind of difficulties at this stage, obviously ask me or ask in the support channel. And then once you are a little bit familiar with how it works and how you're working with that, because once again, it's like a new commands, everything is new, a little bit different. Then take one of these examples. They're very simple. The Vault one probably, or the Faucet one, and try to understand how they're written, try modifying them a little bit, and ask questions along the way. And step by step, we will help you to get to something working.
Awesome. Well, look, Alex, thank you so much for your time this evening. And it's a little bit later for you than it is for us, so we really appreciate it. I'm sure you're off to have either dinner or a beer at this point. I don't know which. But thank you very much for joining us. Really, guys, I'll put the slides up. I'm sure Alex is going to send me those and the video either later tonight or tomorrow. And if you have any questions, you know where to find us. And on the Discord, on email, on Telegram. And again, Alex, thank you very much, and thank you to Beam for your ongoing support.
Thank you.
Awesome.
Great.
Right, guys, have a good evening and see you soon.
Bye-bye.
Bye.